My name is Rob Lee. I'm Marketing Director at RBR. And beside me is Greg Johnson, President, and John Taylor, Sensor Manager. And today we're going to be talking about the RBRtridente and giving you a sneak peek at the RBRquadrante as well. Just a few things before I turn everything over. We're in an operating R&D area here, which is really exciting. You might hear some noise in the background, and that's just the action happening. The other thing is you have a Q&A button on the bottom of your control bar. We're going to use that Q&A to answer questions at the end of the webinar. So if you have any, feel free to put them in. And again, we'll address those at the end. And with that, I'll turn it over to Greg.
Sure. Yeah, it's tempting to show you some of the action, but you know it's all top secret and we can't release that just yet. So you'll have to deduce that from what you're hearing. Good morning, Greg Johnson, coming to you from Ottawa in Canada. We're just entering autumn, and outside the window there are red leaves starting on the trees, so it's transition time again. Very excited this morning to be sharing and officially, I guess, launching the Trident. Which we call Tridente, but sometimes we get away with Trident and we just can't help ourselves. So like most of our instruments, it's got a little bit of an Italian flavor to the name. Used to be always musical instruments. Trident, I'm not sure that there's a, maybe it's like a,
not aware of one.
A Jew's harp or something like that. It could be. And so the Trident really is our first foray into, I guess, after our optode, into active optical sensors, and we're combining 2 fluorometers and a backscatter sensor in a single unit. Here's one in the tradition of all the best cooking shows that we prepared earlier. Quite a small, compact unit in a external pressure case. We want to make sure that the optics are best of breed. We don't use, for instance, any wetted materials, epoxies or anything like that in the optical path, because it's so critical that, that we get really good signal. If I hold it just on the right angle, you'll be able to see the 3 colored filters, but I'm not sure. Oh, look at that, I can almost do it. It reveals my shakes from lack of caffeine in the morning. So we want to make sure that we have a pressure vessel that's good to support this, initially to 2,000 meters and then down to 6,000 meters. And the measurement path is really has immense amount of attention paid to it. John will be talking about that a little bit more, but it also combines what is RBR's DNA, which is very, very low power consumption. And so we really want to have a power signature that is completely unlike anything you've seen before in sensors that have a couple of fluorometers and a backscatter that you might be familiar with. We also want to increase the sampling rate so that this sensor is capable of running anywhere up to 32 Hertz. So quite useful in high-speed profiling applications or dynamic situations. If we try to do a apples to apples equivalent, which is what is sometimes difficult for us and difficult for you when looking at data sheets, we're always trying to find a way of expressing the performance and the power consumption in a way that is easy for you to compare with similar products that are available to you. One figure of merit would be to say that if we're doing a data output rate of 1 Hertz, that we always assume a 12-volt power line, and that's generally typical in the industry. The power consumption, or the current consumption, is about 1.7 milliamps averaged over the second. So 1 Hertz data rate, 1.7 milliamps. The sensor is equipped with our standard kind of 6-pin MCBH on the back. It's got power and ground coming in and RS-232 coming out and in, because you can configure the sensor in a variety of different ways, not least of whether you'd like to poll the sensor and get a measurement on demand, or whether you'd like to have streamed data coming out at whatever data rate you request. The power is our typical wide-ranging input. So although we use 12 volts as our canonical figure for estimating power consumption, we can support anywhere from about 4.5 up to 30 volts. So if you have a 24 volt system, that's fine as well. I guess another way of thinking about that power consumption that I was mentioning earlier is to say that if you're familiar with another device that looks very similar, this consumes 1/20th of the power. That is to say, a 95% reduction. If you add this to our CTD, for instance, on an instrument, you will find almost no impact on the deployment life. And that's really important to us because optical sensors typically are quite power hungry and are something where in the market, people have always suffered that when they want to do an optical measurement, especially any kind of active measurement, then the autonomy of a battery-powered instrument, float, glider, whatever, can suffer directly. So that kind of 95% reduction in power capacity, power consumption, while maintaining best of breed measurement specs is what we're particularly happy with. Some of you already have a sensor similar to this, the EcoPuck from Seabird. We also have an EcoPuck compatibility mode that allows us to put out the data in a format that can be recognized by a glider controller or a float controller or a Campbell logger that's been used to pull the data. That's kind of a brief overview of it. And I'm going to turn it over to John, who's got a little bit to share and some more gory details.
Yeah. All right. Thank you very much, Greg. Yeah, so I figured I'd start off talking about the optical layout for the sensor. I have a slide here that shows a cross section of it. Let me share my screen quickly. All right, so as Greg mentioned, we have 3 different channels. All of them actually have the exact same layout, but we've optimized the design for the backscatter measurement in particular. So over in the lower left here, I have a cross-section view. We have the LED on the bottom left here, and its cone of radiation coming out shown in green. Over to the right of that, we have the detector and its field of view shown in orange. These two are effectively 2 cones that make this intersection here. And this intersection is such that any light coming out from the LED will scatter at angles of 102 to 137 degrees to reach the detector. These 2 cones, as I said, make a measurement volume, and this volume starts at just 0.5 millimeter away from the sensor face and extends to 26 millimeters away.
So John, what's the average of that, like the center beam angle?
Yes, yeah, that's a good point. So it's the average scattering angle would then be 120 degrees.
Okay. And the measurement volume in total?
Yeah, so I also have on the slide here, there's to the right, this isometric view that shows the 2 cones. Yeah. And the section in red is the measurement volume, which equates to about 1.3 milliliters.
Okay.
Yeah. The design is quite customizable. Back to the cross section here, we have the ability to put filters in front of both the detector and the LED if we choose. So we can change the design for any type of parameter. I'll just jump over to a close-up view, Rob, if you can switch the camera for me. So thank you. Yeah, as Greg pointed out, we have the different channels here, and you can see some of the filters that we're using. The center channel here is for the backscatter turbidity measurement. This is the LED on the backscatter side. So it's a 700 nanometer LED. It has a very narrow wavelength range, just 20 nanometer full width half max. There's no filter in front of this one because of its nice narrow radiation. On the detector side, we have a filter that allows it to accept that narrow range of radiation. Next over, we can move over to the chlorophyll channel. We use a 470 nanometer LED, and that also has a 20 nanometer full width half max. On the detector side for there, we accept 700 nanometer center, which is actually a range from, I believe, 675 to about 720 nanometers. Last up, we have the chlorophyll, or sorry, the FDOM channel.
FDOM, CDOM, all those names that keep on getting passed around.
Yeah, that's right. So fluorescing dissolved organic matter. We use a 365 nanometer LED with a very narrow 20 nanometer full width half max. And then we measure at 450 nanometers. And we're sensitive to 425 to 475 nanometers.
Is the geometry the same for all 3 channels, John?
Yes, yeah. So we've mimicked the geometry on all of the channels, so they all have the same profile, but it's primarily optimized for that backscatter measurement. Right. Yeah. I'm going to jump back over to the slides to give a little bit of justification as to why we selected those particular wavelengths. Let me pull up, oops. How do I go back? My apologies. Little operator error here. So first up, I'm showing here a typical excitation and emission matrix for dissolved organic matter. As I pointed out, we're using 365 nanometer LED. So we're exciting the volume with that wavelength, and we're measuring over at 450. This puts us nice into this peak C region of dissolved organic matter. But as we mentioned, we've used the materials and such that we can change the LEDs. So if any of you are interested in other wavelengths, we could certainly target some of the other peaks in this excitation and emission matrix. Next up, just to go back to chlorophyll for a second. So this is an example of what the excitation from, the emission from a chlorophyll signal. So here I'm exciting chlorophyll with 470 nanometer radiation, and this is the emission spectrum that you would see off of a chlorophyll sample. The region in red is the section that the trident is sensitive to, so that 675 to 750 nanometers that I mentioned before. And
John, there have been a couple of discussions in the last year or two about exciting chlorophyll at a different wavelength. What would you do if somebody wants to do that, or to even measure at two different wavelengths?
Yeah, so that's certainly very easy for us to adapt the design to do that. Having the same geometry across and that sort of provision to put filters in wherever we choose. We can easily source LEDs that would be in, say, 440 nanometer wavelength, and depending what your detection range is, if you want to maintain that same sort of nominal 700, we can do that as well.
And FDOM is actually a useful measurement on this device. I know there's been some discussion in the past about CDOM, FDOM measurements sometimes just being discarded.
Yeah, that's right. So actually, that actually leads nicely into the next section where we'll actually talk about the construction of it. Okay. So as Greg mentioned, we're back to the main screen here, I believe. So we have a titanium pressure vessel design, which can be suitable up to 6,000 meters. The windows are made of fused silica, and we chose this material in particular, one for the pressure rating, but also as it permits transmission of ultraviolet radiation. We did look at using color or transparent epoxies and resins. However, those tend to fluoresce with ultraviolet light. And that's a particular problem for dissolved organic matter, because if your signal is fluorescing as it passes through the window, and you're in a slightly turbid environment, you end up scattering that light back to your detector. And if you fluoresce into the range that your detector is sensitive to, it makes for a pretty poor dissolved organic matter measurement.
It's the so-called autofluorescence problem.
Yeah, exactly. Also, resins can discolor over time, so that could manifest as drift in the sensor, and that will require recalibration over time. But thankfully, the fused silica is not susceptible to that. On the topic of drift, so LEDs will drift in their power output over time, and also they'll change their power output over temperature. So I've got a little drawing here showing the internals once again. So we use for our LED, we actually monitor the power output using a reference photodiode. So this allows us to track the power output and compensate the LED accordingly. And also another thing to note is that photodiodes tend to be temperature sensitive.
They're pretty good. They're pretty good thermometers, actually.
Yeah, they are actually. But we add a second thermometer so we can track the temperature of the photodiode and apply appropriate compensation as well.
And that's done inside the instrument?
Yeah, that's correct. So we do all that processing internally. We also have multiple gains so that we can accommodate a very large dynamic range. These gains also allow us to handle up to full sun. And we also calibrate these gains so that we align all the gains so that their offsets are all uniform, and we expose the sensor to a solid standard so we can induce a static, very strong signal and jump our gains. And this allows us to make sure that all the gain slopes are aligned.
Does that mean I need to kind of deal with the data and divide by 10 or divide by 100 as we go along? No,
so that is all done internally. So we do all this processing, and it's all done within about 30 milliseconds. So very, very rapid and quite impressive. Yeah.
If we do say so ourselves.
Yes, if we do say so. So that leads me on to another slide I have here.
You have to share first.
Yeah. Can't seem to get the smoothly jumping back and forth.
Yeah, using Zoom, it's pretty recent phenomenon.
I know. Us old guys have a hard time picking up new tech. There we go. Back in, I believe.
You got it.
Excellent. So here, this is showing all the different measurements we're taking and doing all the different signal processing. So as I mentioned first, I'll start over here with the upper left. We do a reference measurement. So this is that measurement from that reference photodiode that I mentioned. So when the LED is on, we take a reference light measurement. And when the LED is off, we take a dark measurement. We do a subtraction of those two to give us our reference signal. Next, we move over to the detector side. So we take a measurement when the LED is on, and we take a measurement when the LED is off. The measurement when the LED is off is actually very useful because that gives us a measurement of the ambient light in the background. So we can remove any light contamination of our signal.
And that's the fundamentals of the sunlight.
Yes, yeah,
removal.
that. And also during this time, we're doing multiple pulses of light. One, so that we can identify what gain we should be in, so that we can set the unit to the appropriate gain, do multiple measurements in that appropriate gain, and then move on to our next sample. And during this time, when we do this, what we're doing here to measure our detector, we also at this point apply the gain offset and slope correction. Now that we have both our reference signal and our detector signal, we can then move on to combine those two to give our corrected signal. This is when we apply the temperature compensation. So we have that measured temperature from the photodiode, and we apply a temperature scaler that's specific for each channel to give us our normalized corrected signal. So now we have a signal that's compensated for temperature and ambient light, and we've removed any offset or scale that could be induced by the gain. And now with that signal, we can apply our calibration, which converts our corrected signal into whether that's a backscatter measurement, or fluorometry, or a turbidity signal. And
so we're actually producing calibrated output.
Yes, that's correct. So all calibrated data coming out of this unit. Yeah, and it's very impressive that we're doing this on 3 separate channels, and this is all done in only 30 milliseconds and allowing us to produce samples up to 32 hertz. So next up, as we mentioned, very low power. So I have here measurements, our power measurements from one of these units. So this is coming up from a cold start, I guess you would call it. Yeah. So where the unit is unpowered, we give it its 12 volts. You know, in the beginning here, you can see the inrush current and all of our analog circuitry settling. And then later on, we see the pulsing of various LEDs. It takes us only just 91 milliseconds to produce our first sample. And this whole process just consumes a mere 22 millijoules. After this 91 milliseconds, we would go back to sleep. And we're at sleep, we only consume just 9.1 microamps. And the average current across this time, as Greg mentioned, at 1 hertz is just 1.7 milliamps. If you were to sample continuously at 32 hertz, effectively you have this tail end region where we're pulsing the LEDs repeated every 30 seconds. And in that sort of state, we're consuming just 19.7 milliamps.
Might even be repeated every 30 milliseconds.
Sorry. Yeah,
we'll edit that out for you.
Thank you. All right. So we did an equivalent measurement of the sea owl. So the sea owl is a very high sensitivity optical sensor. It does the same 3 channel measurements. It measures backscatter, chlorophyll, and dissolved organic matter. Doing the same where we start from a cold state, we give it 12 volts, and we get our first sample coming out at 1.8 seconds. This uses a whopping 1,688 millijoules, and during this time, it's pulling an average current of 69 milliamps. The unit doesn't go back to sleep. It just kind of continues on at the 69 milliamps, producing a reading every second. Flip back to the main camera here. So just to summarize, we've got our backscatter, turbidity, chlorophyll, and FDOM sensor here. Thank you. Too many cameras in front of me to track them all. The backscatter measurement, we have a limited detection of 1 × 10⁻⁴ inverse meters. We calibrate this across a range of 0 to 5 inverse meters. This gives an effective resolution of just shy of 16 bits. For turbidity measurement, our limit detection is down to 0.001 FTU, and we calibrate across a range of 0 to 500 FTU.
So when you say turbidity and backscatter, that's because the sensor is actually available with both, in either configuration.
Yes, yeah. So the optics are effectively the same. It's just we calibrate to a different range.
Right.
Yeah, and
is the calibration range kind of like it saturates at that point, clips?
No, so it'll continue on measuring. We know the linear range for turbidity is 0 to 500 FTU for certain, and for backscatter, we calibrate to that range because that's where we have a good standard. Yeah. But yeah, it can continue on measuring because we have all these gains to be able to detect a much stronger signal. But at that point, we're sort of out of our calibrated range. Yeah, and so for that turbidity measurement, that equates to just about 19 bits of resolution. Next up, for the chlorophyll channel, we have a limited detection of 0.01 micrograms per liter, and we calibrate across a range of 0 to 25 micrograms per liter. That's just over 11 bits of resolution. And lastly, we have the dissolved organic matter measurement. So that has a limited detection of 0.005 parts per billion, and we calibrate across a range of 0 to 500 parts per billion, and that's once again about 16 bits of resolution. Yeah. And so, as Greg mentioned, this can operate as a standalone sensor, with its being streamed or pulled. We can also integrate it onto a logger like we have here.
Let me do something.
Okay, fine. Yeah, our hand model. It can be integrated onto one of our CTDs and stream the data and be logged there. Yeah, it's quite a versatile package.
Mm-hmm.
Yeah.
The pricing for this is announced. It's under $10,000 US. And in your local currencies, we've got some pricing. Obviously, there's Euro price and RMB price, Canadian dollars as well for Canadian customers, of course. But that's quite different from what you're used to. We want to provide something that really does excel in terms of performance, power consumption, but also the economics. There's no justification to have something that's more expensive than that. And availability, we are starting to ramp up production right now. So first shipments are going out. I would say general availability will be near the back end of this year. So lead times at the moment are terrible and embarrassing for us at RBR. We've historically been at 4 to 6 weeks. Mm-hmm. Supply chain, as you might have heard, is a little difficult globally. And so at the moment, it's considerably longer than that. So if you've got pressing needs for deployment in January, February, now is the time to be talking to us, making sure that we can get that through the pipeline. While we're here, I guess I'm going to show you one other thing that we've got kind of coming up. We have made this rather ungainly Medusa. I don't think that's an official name. Marketing will take me to task on that later. This is our Maestro. So our Maestro is a 10-channel multi-parameter instrument. This one's got a CTD and oxygen on the front, but we've also attached power and 3 of our narrowband radiometers, which I won't bother pulling the caps off of. These narrowband radiometers are kind of 15 nanometers and can be available in whatever wavelengths that you're interested in. And signal to noise is very nice on them, about 5.5 decades or so. However, this many cables and connectors is, as you know, it's always the point of failure in instruments. And we really wanted to combine that together to make a more convenient unit. So I can drop that in your hands and show off on the close camera, maybe, Rob. So people have seen the Tridente, and here is our quadrant or quadrante, which rolls off the tongue even less likely, but it shows my Italian heritage. And so this is 4 passive optical sensors. Power plus 3 narrowband radiometers, or you could have 4 narrowband radiometers. We're able to configure it in any mode there. The dynamic range for this is about 5.5 decades for power, just over 5 decades exactly for the radiometers. And that gives you a kind of resolution of somewhere around 0.0002% of full scale. Again, this won't clip in full sun, and so it's able to be used all the way up to the surface, pointing at the sun, and then being dropped down through the water column. And that is also available on the same time scale. I guess we can go back to the main camera, and John and I are both a little hopped up. No, we can't say hopped up, caffeinated up.
Yes.
So we've run about twice as fast as we might have otherwise. But we're happy to take some questions. And I see a couple that have come through.
Yep.
So let's have a look. The first one that we see. Can the sensor, and we're talking about the Trident, can it be adapted to measure crude, similar to the CL? Yes, absolutely. So we are able to support phycocyanin, phycoerythrin, rhodamine, fluorescence, crudes, optical brighteners, basically anything across the range. Crudes generally need a slight UV crossing excitation, but the emission still within the wavelength of a silicon photodiode. And so we're able to do that.
So the fused silica windows can permit transmission, I think, just above 200 nanometers of radiation. So it can easily accommodate LEDs down to that short wavelength.
Above, down to, longer than, shorter than, you know, all these things.
All the directions.
But given that visible ends at about 400, 200 is what we're going to call reasonably deep UV. Question from Warren. Solid standards. So will we have solid standards for standard measures like chlorophyll, or a similar system for calibration checks, or is the calibration stable over time? First of all, John, actually, we talked about the calibration, but we didn't really talk about the standards that we're using to calibrate. So why don't you start with that, and then we'll talk about Warren's question about how people can do these checks in the field.
Right. Yeah, certainly. So for chlorophyll, we're actually using acetone extracted chlorophyll as our primary standard. We use internally in the house, we have a fluorometric spectrophotometer, which is actually what I use to produce that chlorophyll graph I showed there. So we can do a dilution series of this chlorophyll standard to get essentially the amplitude signal from all the different concentrations across a range of chlorophyll. And we then calibrate it in a working solution, a dye such as fluorescence. We then use the same optical configuration on the fluorometric spectrophotometer to measure the fluorescence signal and derive effectively a chlorophyll equivalent fluorescence concentration, and then we calibrate the unit in that solution.
Really as a transfer standard.
Yes, yeah, exactly. So solid standards, we haven't planned to ship any with the unit, but for that gain calibration that I mentioned, we are using fluorescing acrylic to induce a static signal. For solid standards, of course, it's very important to have the alignment just right, because if you move it around, you'll change the signal. And in that very first slide I showed, the unit has a very small volume of measurement. So if you were to move that solid standard anywhere in there, you would see shifts. But certainly, if we wanted to, you could make a little jig perhaps and get a fairly stable signal. It could be used to kind of track the health of the sensor. I don't know if I would necessarily commit to using that for checking the calibration state. Perhaps using another solution would be more appropriate. There's lots available, or perhaps we could work out something where we could provide something like that.
Of course, for basic functionality, to make sure the instrument's running, some of the light is visible, and that which isn't, often you can get an indication using even a Kim wipe. There's a great kind of fluorescence sensor.
Paper and cellulose, it fluoresces very well, and you'll also get a signal off the backscatter and from the dissolved organic matter channel as well.
Another question from Philippa. Thank you for the first comment. It's complimentary, so I won't read it out because we're trying not to be let our heads grow. Do we have methods for biofiling? Yes, so we have wipers available that will brush the top surface periodically. We actually use the Zebratech that comes out of New Zealand, Zebratech wiper that's been used for, hundreds of different sensors over the years. You can also, of course, put copper tape around the peripheral areas of the sensor. It won't work very well if you put copper tape over the optical elements. So that will help mitigate as well. So at the moment, the kind of active techniques are the most successful ones. You will usually see the fouling signal quite clearly, particularly in chlorophyll. Surprise, surprise.
And that same wiper will work just as well on the quadrant as well.
That's right. And we have clamps that will allow you to use a wiper and extend that brushing range over a larger kind of sector, which allows you to use a single wiper to brush many different sensors. Looks like there's a second part of the question.
Oh, the one you mentioned, the copper plate.
Oh, there we go. Sorry, I hadn't even read that part, but great minds think alike and fools, blah, blah, blah. Looks like you have some holes on a metal plate. So it's not actually holes, although that probably appears that way over the camera. These are flush mounted. And so I can detect with my finger very, very slight changes where I transition from titanium to the silica, fused silica. So they're not recessed and there aren't big kind of nucleation sites, more importantly. Tested in the field, yes. However, we have been asking some of our more esteemed colleagues to do those tests in the field, and we're still pending kind of approval to publish those results. So we're not able to do that at the moment. And I probably shouldn't put those people on the spot, but they're people that you're all familiar with. And there are about 10 units at the moment that are going through various stages of testing around the world to be able to show the kind of both lab performance in individuals' controlled environments and marine integrations, both integrations into the CTD, but also kind of ad hoc integrations into floats and gliders. This is a drop-in in terms of form factor compatibility with holes that were made for eco-pucks. And there is a flange available for a dry bay type mounting situation if you would like to do that. Can the sensor be used for more deployments as well as profilers? Yes, indeed. So we don't bother differentiating in our sensor as to which one. The sensor doesn't have any awareness nor any particular characteristics that make it more suitable for one than the other than the sampling rate that you're running at. So one of the tricks to achieving this very low power consumption is that we're running at 32 Hertz, but we only run at 32 Hertz once for one sample, and then we go to sleep. So in a mode situation where you're running at 1 Hertz or slower, we're still only awake for the equivalent of taking one measurement. If we wish to be in a profiling mode with dynamic situation, then we run at powers of 2, basically, aren't they?
2, 4, 8, 16, 32.
And do we support the 24? We
Maybe
sometimes
there's
have a
a
24 in there. 24 makes it compatible with some other CTDs that run at non-standard rates. And thank you, Lindsay. Actually, I think you guys can't see each other's questions, but Lindsay asked the same question about a wiper for fouling, which I think we just addressed.
Exactly.
That looks like
we just got one more.
Oh, yes. Adam, temperature gradients. Very good question. Yes. So the reason that we've got this thermistor right next to the photodiode is so that we are compensating for that most sensitive element directly and independent of the thermal mass of not only the pressure vessel itself, but also the vehicle. Because the vehicle is, those dynamics are kind of unknown to us. We want to make a sensor that's tolerant or agnostic of any deployment situation. And so rather than saying that we need to have certain awareness of what the gradient is, we simply measure the instantaneous temperature. You've done quite a lot of plunge tests where we've been inducing step changes.
Exactly.
And I guess that was optimizing really where this thermistor sat.
Yeah, certainly, because you get a lot more heat transfer through the front end, so the electronics will typically be a slightly different temperature. So we situate the thermistor as close as we can to the photodiode, and it's sort of effectively coupled by the copper inside the PCBs there, so that we have a nice tracking of the photodiode temperature as it's moving through, and that's the primary effect of the temperature effect on the signal.
And so if the sensor is flush mounted in the skin of a vehicle, or if it's got water flowing over the entire thing, it doesn't really matter. We're just measuring the most sensitive element.
Exactly.
So our datasheet specs all include that temperature compensation. It's not a spec for a particular temperature. It's taking into account that we are correcting for temperature all the time. I think that's probably enough for now. It's 11:35. Rob's going to come over and kick us off.
That was great, guys. Thanks very much. Just one follow-up question on the RBRtridente. We didn't talk about availability of information or availability on that one too much.
Yep.
It's more.
It'll be on the same time scale as the Trident.
Wonderful. Okay. And if you go to rbrglobal.com, we'll have more information up on the website about that one.
Just don't forget the dash in the middle.
As
dash.
as well. Yes. Okay. And which brings me to, so we're going to have a recording of this webinar available on rbr-global.com. And we'll also be sending that out to all registrants following the webinar and over the next couple of days. We'll also be sending out some related goodies to you as well. If you have
this is the first I've heard of it.
If you have any questions at all, or if you want to talk about your particular application, get in touch with us at info@rbr-global.com, or again, go to our website at rbr-global.com. And again, thanks very much for joining us, and thanks very much, guys. Very informative.
Pleasure,
Appreciate it very much.
Good.
Have a great day, everyone.
Ciao.
Bye.